Over to you, sir.
Very good evening, each and everyone. So let us now start our talk. And I'm just sharing the PPT. I hope you are able to view me as well as listen me also.
So we can hear you, but the screen is not shared, I guess.
Screen I have not shared till now.
Yes, now you are visible, sir.
Okay, now I'm visible. Okay.
Yes.
So there was some problem with the camera, it seems earlier. Okay, so I'm just sharing my screen now. So once again, good evening to all of you, and let us start our topic. And the topic, as it was indicated in the schedule also, that is the feature engineering. This will be the flow of my talk. And the first one is the difference in the data mining and machine learning. So definitely you may be just thinking of that why it is so, but because we are talking of a feature engineering, and feature engineering is very much related to the data mining and machine learning. And I have seen that usually the people are confused between the data mining and machine learning. So I thought let us start with the data mining and machine learning. Then I will just discuss what is feature engineering. And then I will discuss about the dimensionality reduction, the feature subset selection, the feature creation, and the handling of the missing values also. Some 2-3 slides are there only for the handling of the missing values. And a lot of other things are also there in the feature engineering. But given the time that we have only 1.5 hours, keep the laptop in which we mostly use very frequently, and rest of the other things are also there.
All the participants, please mute your. Yeah, thank you.
So definitely few more things are also there in the feature engineering, but because of our time, we won't go through details of each and every one. So let us just take first 2 or 3 slides about the difference in the data mining and machine learning. Usually, sometimes the question is asked that what is the difference between the two, if there is any, and people find it very difficult to differentiate between these two. So the first 2-3 slides are for this. That is, what is the difference in the data mining and machine learning? So data mining and machine learning are the two distinct but related fields in the realm of data analysis. So the sentence basically consists of the one important point, that is basically the data analysis, and the other two adjectives are basically the distinct and the related. So now it is very clear that the data mining and the machine learning, they both basically deal with the analysis of the data. It means they are basically the tools for the data analytics, and we say that they are distinct but they are related also. So sometimes it seems as if it's confusing that they are distinct, they are different, it means, but they are related also, but they both are in the data analysis. So when we go through in the detail of the slide, the things will be very clear. So while there is some overlap between, they have different focus and goals. So the second sentence make it little bit more clear. And what is written here is that though there is some overlap between them, that there is something common between them, because we say that they are related, but they have the different focus and goals, but their focus and the goals are completely different. And that is why we say that they are distinct. So there is some overlap, but their focus and goals are distinct. So that is why we say that they are distinct as well as they are related to. But definitely with these two lines, nothing is more clear. So let us take something that what is basically the data mining and that what is the machine learning. And then we can just come to a conclusion that what is our conclusion as far as the difference in the data mining and machine learning is concerned. So what is written here about the data mining? That data mining is the process of discovering patterns, relationships, and insights from the large data sets. So what basically we do primarily in the data mining? In data mining, basically we discover the patterns, relationships, and the other insights. And we usually call that we are trying to gain the knowledge which is inherited in the data sets, but which is not open, which is not quite obvious, which is not quite open. So trying to find out the hidden treasure or the hidden information, hidden patterns, etc. in the data set through the algorithmic pattern or the algorithmic way, or through the use of algorithms and other visualization techniques, etc. So that is basically the data mining. So getting the patterns and the relationship, that is basically a data mining. It involves extracting knowledge or information from the data using various techniques such as statistical analysis, pattern recognition, and visualization. As I told you earlier, that we use basically the computational tools or the visualization tools to find out that what is basically the knowledge or the information which is inherently hidden into the data objects. The primary objective of the data mining is to identify the hidden patterns, trends, and correlation within the data that can be useful for making informed decision and predictions. So I think this last sentence is rather a little bit more clear. Here we say that what is the primary objective of a data mining, and this is basically nothing but just extension of what is written here in the first sentence, and that is it is used basically to identify the hidden patterns and the trends or the correlations between the data objects, etc., so that we can take a more informed decisions or a predictions. So data mining typically follows three steps. So as far as the data mining is concerned, it consists of the data pre-processing, the pattern discovery, and the evaluation and interpretation. And then there is no heading for this, so it is written here in the normal form. So let us take each one by one, that what are these steps basically. So the data pre-processing is that the cleaning and preparing the data for analysis by removing noise, handling missing values, and transforming the data into the suitable format. What we are writing here, whatever the data set that is available to us, from whatever the source you take the data, even if it is generated from the modern devices, there will be some problem with the data. Even now, even today also, it is very difficult that we will get a completely pure data that will always be ready for our algorithms, so that we can apply the data mining algorithms on it. And for the simple reason is that the different data mining algorithms take the input in a different format. So if nothing else is there, at least we will have to reformat the data so that the data is input ready for the algorithm which we want to use. But additionally, that is only a one thing. Additionally, a lot of uh, problems will be with the data. There may be some missing values, there may be some noise, and a lot of other problems are there. So we have a one step, and that we call as a data pre-processing step. And the job of the data pre-processing step is that it reduces it changed the two things are there. The one is that it make the data pure. It makes the data pure means whatever the noise, missing values, and other problems are there in the data, it is removed. And the second is that if it is required to reformat the data, it reformats the data according to the algorithm. So basically there are two objectives of the data pre-processing step. And whatever we are going to discuss today, that is the feature engineering, that is actually related to the pre-processing. Okay, so slowly you will just see that why I'm discussing all these things. So the feature engineering is related basically to the pre-processing, because what we do in the feature engineering is that we transform the data in such a way that it is pure as well as ready to be used with the algorithm. Then once the pre-processing has been done, then we can apply the data mining algorithms on the data after the pre-processing, and to discover basically the patterns. Okay, the pattern, trend, or whatever analysis we want to do. So that is written here as a pattern discovery. So applying algorithms means the data mining algorithms, applying algorithms and techniques to identify the patterns, relationship, or the anomalies in the data set. So identify patterns, relationships, anomalies, etc. These are basically the job of the data mining, that what type of data mining operations we want to perform. So different algorithms are there for the different tasks. So these are different variety of the tasks, nothing else. So that is basically the actual algorithm that we use for the our job, I mean for the data mining. Then the evaluation and interpretation. So definitely we have the input, we have the algorithm. So the input is applied to the algorithm. Obviously it will generate some output. So now we have the output. So how this output will be basically evaluated, how to interpret, how to see that what is the meaning of our output. So that is basically the next step, and that is written here as the evaluation and the interpretation. So assessing the discovered patterns for their usefulness, reliability, and the significance, interpreting and visualizing the result to gain the insights. So whatever the output that will be generated from the algorithms, it is not necessary that each and every output is basically useful for us and we would like to use them. Few of the output may be, for example, if you go for the association and correlations, etc., few will be useful and few may not be useful. So basically now we need to see that what is the output, how to visualize the output, and try to distinguish that which of the patterns are useful, and we can use it for any decision making or prediction or anything basically, and the others which are not useful, or you say useless. So differentiating between the useful and the useless results, that is basically the evaluation and interpretation. So in that way, if you see, the three steps make a process complete. That first we need to go for the pre-processing, then the pattern discovery, and then the evaluation or interpretation of the output. Data mining techniques can be used across various domains such as market research, fraud detection, customer segmentation, and recommendation system. It does not necessarily involve building predictive models, but rather focuses on extracting knowledge from the data. So it simply says here that where we can use basically the data mining algorithms. And the last line, which is really more important, and that is, it does not necessarily involve building predictive models. And you will see that in case of the machine learning, we will see, or we will discuss, that it makes basically the predictive model. And here we say that in case of a data mining, it is not necessary that it will make the predictive model, but rather what it does, it means data mining. But the data mining focuses on extracting the knowledge from the data. So if you see this particular slide, so what we are focusing here in case of the data mining is that the data mining basically focuses on extracting the knowledge or the information from the data, and not for building a model from the data as such. Okay, but whatever may be, these are the steps which are basically used for the data mining, for the using of a data mining algorithm on a large data set. Then in the next one, we just discuss here that what is basically a machine learning. So what is written here is that the machine learning, on the other hand, is a subset of artificial intelligence that involves the development of algorithms and models that can automatically learn and improve from experience or data. Now we see that here it is written that the machine learning is basically a subset of artificial intelligence. And whenever we say that artificial intelligence, the simple meaning is that these are basically the algorithms which learn from the data. When we say which learns from the data, means basically from the past data or the experience. So the same thing is basically written here, because that is the general principle for the AI. So that is why it is written that the machine learning is basically a subset of the AI that involves the development of algorithms and models that can automatically learn and improve. So the important point is basically that can learn and improve from the experience or the data. The primary goal of the machine learning is to enable the computers to learn and make predictions or the decisions without being explicitly programmed. So if you see this sentence, it is basically taken from the machine learning book of the Mitchell, and it says very explicitly in this way. And this is a very common definition of a machine learning, that the machine is not explicitly programmed for this, but machine means the actual program we are talking of, but it learns basically. So, and it changes. So that is basically the machine learning. So it also plays basically with the data. And here also the main crux is the data. In case of the data mining, also the main crux is basically the data, because we are playing with the data, whether it's a machine learning or whether it's basically a data mining. Machine learning typically involves the following steps. And what are the typical steps in the machine learning? The data collection, gathering a data set that contains the input features and their corresponding output target values. So we need to know about the data. So the data is basically there in the data mining also. This step was not written there, but it doesn't mean that we are playing in the air. Definitely the data has to be there. And if the data is there, it must have been collected from somewhere. So the next step is basically the data pre-processing. So you see that this step is exactly same, the cleaning, transforming, and preparing the data for a training model. So it's basically exactly same. So whatever the data is there, because the property of the data is not going to change, we will collect the data from the different sources, and whatever the errors, and error may be because of various reasons, maybe calibration, maybe the instrumentation, and a lot of other problems may be there. So for those problems, we need to basically go for the pre-processing. So if there is a data, so the pre-processing step is must. And whenever we are talking of a pre-processing, it means we are talking of feature engineering, basically a one part of the data pre-processing. I don't say that the feature engineering is the data pre-processing. I say that feature engineering is a part of the data pre-processing. Then we say the model training. So as I just told you that basically in the machine learning, what we do is that we just make a model. So that is basically the training of a model. So using the prepared data to build a model by applying an appropriate machine learning algorithm. So we use basically the machine learning algorithm and we prepare a one model out of it. And then we just evaluate that model, because how accurate that model is, whether it will give me the actual prediction or the correct predictions or the not. So for that, obviously we need to evaluate the model, because from it is not possible that from the data we can make only a one model for a one task. The several variety of the models can be made. So if it is possible to make a multiple models from the data for the same task, then which particular model is more better? Which particular model is more better means which is giving me the more accurate results. So for that, obviously, we will have to evaluate the model, that whether really the model is good or not. So because of this reason, the model evaluation is an important strategy, so that we can fix that, yes, this model is more appropriate for this particular data, this task on this data. Then we have the model deployment. So applying the trained model to make the predictions or the decisions on the new unseen data. So once we have evaluated the different models, then we will choose a one particular model which is more accurate, which is better, which we will prefer. And obviously it's a decision maker's job. He will just see that which model is better. And then the model will be used basically for the predictions on the unknown data. So machine learning algorithms can be broadly categorized into the supervised learning and the unsupervised learning. The supervised learning is that where the model learns from the labeled examples. Labeled examples means that a set of the input and the output both are there, and with the help of the input output pair, the algorithm learns that what is the actual model. And in case of the unsupervised model, we have basically a unlabeled data. It means that only there is no target variable, or there is no, you can say, output. So only the input set is there. So with the input set, it learns on its own. So those who have gone through a supervised and the unsupervised learning, definitely they may be they may have understood it very easily. For others, it may be difficult, but because of a time, it is not possible that I can go in detail of everything. So just simply remember that in case of a supervised learning, we have the target variable also, which usually people call as a output. So a relationship is found between the input and the output. Input means the other variables or the features by which we will make the model for the output variable. And in case of the unsupervised, we do not have basically the output variable. We have only the features or the input variables, and with that we make the model. Machine learning is commonly used for the tasks such as the classification, regression, clustering, and the recommendation system. So for what we use it, that is written here, and the same was written there in the previous slide also, that for what type of the task the machine data mining algorithms are basically used. So this slide is basically rather more important in a way, that how you can differentiate between the data mining and machine learning is that, in summary, while the data mining focuses on extracting the knowledge and the patterns from the data, the machine learning emphasizes the development of algorithms and the models that can automatically learn and make predictions or decisions. So I think now the meaning is rather more clear, that in case of a data mining, we basically focus on extracting the knowledge and the pattern from the data. But in case of the machine learning, we emphasize basically on the development of algorithms. And when we say the algorithms, basically they are nothing but the models, or you say the models are also the algorithms, because basically the model is nothing but algorithm will create basically a model. So either you use the word algorithm or the model, they both are basically synonym to each other as far as our this talk is concerned. So machine learning emphasizes the development of algorithm or the model that can automatically learn and make predictions or the decisions on the unknown data. So data mining is a broader field encompassing various techniques, while the machine learning is a subset of a data mining that involves building predictive model. So the second sentence is rather more elaborative way to explain the difference between the data mining and the machine learning. And it very clearly says that actually the machine learning is a subset of the data mining. Rather, data mining is basically a more broader field which inculcate or which includes a lot of other aspects also. And machine learning is basically just thinking of a predictive model from the data which is available to us. So the data mining is basically a superset of the machine learning, or you say that machine learning is basically a subset of a data mining. But whatever may be the case, because both are related to each other in a way that they both play with the data, and the data is not very accurate, and it is not in the format. Okay, just leave about the format right now, because in case of the feature engineering, we are not at all going to discuss about the formatting. So I'm just leaving this formatting topic here only. So I will simply say now onward that the data is not accurate. Not accurate, I mean to say that data is impure. So what we do is that we want to make the data pure in the data pre-processing step. And this feature engineering basically is a one aspect that can be used to make the data pure, so that we can apply it in the algorithm. It means data in the algorithm. Okay, so why basically we are going for the feature engineering is now very clear. So now let us take one or two more slides for the feature engineering, that what the feature engineering is. So the topic of the slide is basically what is feature engineering. So feature engineering is a process of selecting, creating, or transforming the input variables or features in a data set to improve the performance and effectiveness of the machine learning models. And why we are doing it? Just give me a 1 minute. Huh. वो अमन को बोल देना कि वो सारा काम कर ले, मेरी क्लास चल रही है, मैं बाद में आता हूँ. Sorry for disturbance. So what we do basically in case of the feature engineering is that we select, create, and transform the input variables. Input variables means basically the features in a data set. Okay, we will just see in detail that select, create, and transform feature set. But why we do it? We do it to improve the performance and effectiveness of the machine learning models. So basically, in feature engineering, what we do is that we play basically with the features. Why we play with the features? We play with the features so that we create a group of the features on which the performance of the machine learning model will be more better. So it means that basically we will do something with the features. And when we say the features means basically the data set, because the data set is given in form of the feature, that the feature 1, feature 2, feature 3. Obviously, each object will be defined by n number of features. So if there are n number of features, so how to play with the features so that the output of the actual algorithm, that is basically the machine learning algorithm, is uh, per, uh, is more effective, or its performance is enhanced. That is basically the feature engineering. It involves leveraging domain knowledge, data understanding, and creativity to extract relevant information from the information and create meaningful features that can enhance the model's power. So what is the second sentence? The second sentence simply says that what you require to for the feature engineering, if you have to play with the features, so what knowledge or what understanding is required? So you need to know about the domain knowledge. So if you have the domain knowledge means that data is related to obviously some aspect of the life, maybe related to agriculture, related to environment, related to say anything, maybe some industry, some process. So if the person is having a particular domain knowledge, suppose if the data is related to agriculture, and if the person is very good in the agriculture, so he will be able to understand the data in a much better way than the other person who doesn't know anything about the agriculture. So that is the meaning of a domain knowledge. So if you have a domain knowledge, obviously you can understand the data in a more better way. And then the data understanding, you should have some automatic tools by which you will be able to analyze the data. When we say the data understanding, it doesn't mean that you have to understand the data by viewing or seeing it. We say basically some tools. The tools may be a simple statistical model, for example, the correlation or something else. So it may be any simple statistical tool to some complex algorithm so that you can understand the data. And the creativity to extract the relevant information and to find out that which data is relevant and which is not, and take particular data. So it tells here, this first paragraph, that what basically the feature engineering is, and if we have to go for the feature engineering, what what knowledge or expertise you should have. The quality and the relevance of the features used in a machine learning model can significantly impact its performance. Definitely, it has been said in the first sentence here itself, and you or otherwise, I should say that you can guess it very easily, because we are going for the feature engineering. It means we want to play with the features. Why? Because the relevancy of the features is very much important for the performance of the algorithm. So that is written here, that the quality and the relevance of the features used for the machine learning model can significantly impact its performance. Means the performance of the machine learning model is highly affected by the quality and the relevance of the features. Okay, so the feature engineering aims to identify and construct the informative features that can capture the underlying patterns and relationships in the data. So what we do is, in case of the feature engineering, we try to play with the features in such a way that find out the more informative features by which the performance of the algorithm will be enhanced. And it involves several techniques, including, for example, so the feature selection, identifying what is there in the feature selection, identifying the most relevant subset of features from the available set. This can involve techniques such as statistical test, correlation analysis, or the domain expertise to determine which features are most informative for the target variable. So as the name indicates, the feature selection, with the n number of features which are given to represent the data, we try to find out a smaller subset, that is m. So here the m is smaller than n. Okay, so we try to find out a subset of the features on which my algorithm will be able to give rather a more better result, or at least as good as on the full data set. So if I'm using the n data, not full data set, I mean to say full feature set. So if on the full feature set, I'm getting some accuracy by the algorithm, and on a reduced feature set, if I'm getting the same output or maybe a better output, or you rather say that even if not the better, but the same output, then definitely it is better that I must go for the reduced feature set, because in that case, what will happen? My computational complexity will be basically better. In a very short time, I will be able to get the results. So wastage of the computational power, energy, human resource, that all will not be there. So that is basically the feature selection. The feature extraction is, feature selection means that finding a subset of a feature. We do not create the new features, but few features are basically eliminated and a subset is found. Okay, so that is basically the feature selection. The feature extraction, creating the new features by transforming or combining the existing ones. So I think by now the difference between the feature selection and the feature extraction is very clear, that in case of the feature extraction, we create the new features. And how we create the new features? By transforming or combining the existing ones. It means we not only find the a smaller set, or you say the subset of the features, by eliminating few of the irrelevant or redundant features, but rather we combine or transform the features into, say for example, two features will be clubbed into a one new feature. So these two can be eliminated and the one new feature will be added. So the total number of features, earlier if it was n, now it will be n minus 1. So definitely we have reduced. So in this way, a lot of reduction can be done. So the difference in case of the feature selection and the feature extraction is that in case of the selection, we do not create a new feature, we only form a subset. And here the feature is reduced basically by transforming or combining the existing features. This can involve mathematical operations, scaling, binning, aggregation, or dimensional reduction techniques like the PCA or the TSNE. So the PCA is basically the principal component analysis, or the TSNE is the T-distributed stochastic neighbor embedding. Obviously, we do not have time to go into detail of all these. It simply says that someone who is more interested can go or search on the internet that what all these methods are, or they are given in almost any general book which discuss about the machine learning. So you can go through it. Then, okay, in general, whenever we talk of a feature engineering, usually what happens is that the people think of that either the feature selection or the feature extraction is only what comes into the feature engineering. But it is not so that only these two comes into the feature engineering, but rather handling the missing values or the missing data also is basically a part of the feature engineering. So that is written here. The third aspect of the feature engineering is handling the missing data. So dealing with the missing values in the data set by imputing or filling in the missing values using the various strategies such as the mean imputation. Imputation means the filling, mean imputation, the median imputation, or more advanced techniques like regression imputation or the multiple imputation. So what it simply says that how to handle the missing values. And as I told you that I will just discuss in 2-3 slides that how to handle the missing values. So we will see few things there also. It's only for the general discussion purpose that what basically comes into the feature engineering. Encoding the categorical variables, as the name indicates. I think I think most of you obviously must be, because you are here in this course, so you would be working either in the data mining field or in the machine learning field. So most of the you people may be knowing categorical variables, numerical variables, and is ratio variables, etc. All these. So uh, I'm just discussing the one that is encoding the categorical variable. So encoding means that categorical variable means the categorical variables will be encoded in some form. And in some form means basically because it is categorical. So when we will code it, so we will code it basically into the numerical form. So when we say the encoding categorical variable means representing the categorical variables into the number form. So that is written here, that converting the categorical variables into numerical representations that can be processed by machine learning models. So that is the encoding of a categorical variables. This can be done by using techniques like the one hot encoding, ordinal encoding, or the target encoding, etc. So definitely I'm not going to these encoding schemes or techniques, but you can understand here, for example, if there is only say two suppose there is some feature which is binary in nature, so its value can be either yes or no. For example, we are going for the medical diagnostic test. So suppose there is a problem, so the problem will be there or the problem will not be there, either it will be yes or no. So what we can do is, when I say the and obviously it's an encoding variable, so what I can do is I say that I will encode it in the numerical value. So what I can do, I may choose, for example, 1 and 0. So 1 may represent, for example, the yes, and the 0 may represent no. So wherever the yes and no is written, I will just simply write 1 and 0 in this place. So that is the encoding of the categorical variables. And it is not necessary only for the binary. Even if it is non-binary in nature, for example, the colors are there. And suppose a color is a one variable, and there are 5 different colors are possible. Suppose red, green, blue, yellow, and magenta. So what I can do is I can just take 1 for the red, 2 for the blue, 3 for the green, 4 for the yellow, and say 5 for the magenta. So wherever the magenta is there, it will be replaced by the 5. Wherever the yellow is there, it will be replaced by 4, and so on. So that is basically encoding of a categorical variables. Then normalization and scaling. So rescaling features to ensure that they are on a similar scale. This can help prevent certain features from dominating others during the learning process. The common techniques include standardization or the min-max scaling. So here also few names are written here. I'm not going into detail of this. I simply want to tell you that what is basically the normalization and scaling and why it is required. So suppose, for example, if we have the two features, so one is, for example, is a age, and the another is, for example, say salary. So age value will be, say, for example, 1 to say maximum 100 or maybe 120, 125 or so. But if you just look for the salary, so the range of the salary may be, for example, the 5,000 to say on monthly basis, say maybe 10 lakhs or 15 lakhs or so. So you see that the range of the one value is between say 0 to 120 only. So only this much is the range, and the other range basically starts from the 5,000 to say 15 lakhs. So if suppose we need to find out distance or difference between the two data objects on the basis of this age and the salary. So the salary range is so high that it will overwhelm basically the age. When I say it will overwhelm the age, it means whatever the decisions will be taken here, actually it will be on the basis, it will be on the basis of salary only, and age will have no say because the range is very small or very less. So what we would like to do is we would like to represent the salary as well as the age on the same label, on the same platform. Say, for example, I want to take it into the 0 to 1 scale. So the salary also will be put into the 0 to 1 scale, and the age that is in the 0 to 120 will also be put into the 0 to 1. So now because they both are into the 0 to 1 scale, so they will have the equal effect. So whatever the decision will be taken now, it will be basically because of the both and not because of the salary only. So in such cases where there is a great difference in the ranges of the different features, so the normalization and scaling is required. Then handling the outliers, a lot of algorithms are there which are very much susceptible to the outliers. And the definition of outliers is basically very simple. Most of the data you will find basically it follows some pattern, and there may be a very few data which doesn't follow the pattern. So any particular data object which does not follow the pattern, we call that as an outlier. And if you take any data object if you take any data series, anything if you take, so you will just find out, if you have gone through a course of statistics and probability in statistics, so you may be knowing that any data set basically follow some distribution. Bernoulli distribution, lot of distributions are Gaussian distribution, lot of distributions are there. So it means it follow, basically when we say that it follow the distribution, means it follows basically a pattern. So anything which is very much different from the normal pattern, that is basically the outlier. And there are a lot of algorithms which are very much susceptible to the outliers, means if the outlier data objects are there into the data, in the input data set, then the output of the algorithm may not be that good. The output will be compromised of the algorithm. So that is why it is necessary for at least those algorithms to remove the outliers completely. So handling the outliers is also basically comes into the feature engineering. So what is written here? Detecting and deleting, and dealing with the outliers, which are data points that significantly deviate from the normal pattern of the data. Outliers can be handled by removing them, transforming them, or replacing them with more representative values. So this basically tells that what are the different ways in which you can handle the outliers. Then for the time-based features, I mean for the time series data, incorporating the time-related information into the data set, such as the date, time, or seasonality, etc., which can provide additional context or the patterns for the time series or the temporal analysis tasks. So it is better. So you just see that it is not so that only the feature selection and the feature restriction is a part of the feature engineering, but rather when we say the feature engineering, it is a much broader we should think of as a much broader sense. And all these things like the feature extraction, selection, handling of the missing values, handling of the outliers, normalization and scaling, and the encoding of categorical values, all these basically come into the feature engineering. But as I told you that we do have only 1.5 hours, so we cannot go for each and everything. So what I will do is that I will be discussing today the feature selection, feature extraction, and the handling of the missing data or the missing values only. Okay. So now we come to the, as I told you that the basically it's a data pre-processing task. So there are, I mean, feature engineering is basically a pre-processing, data pre-processing, one of the pre-processing steps. So it is written here that basically why we go for it. Okay. So there are a variety of benefits to dimensionality reduction. And when, and as I told you that we are basically discussing here the feature selection, feature extraction, and the handling of the missing data. If you take the first two, so this is basically the reduction of our dimensionality, that we want to reduce the dimensions, means basically the number of features. We want to reduce the number of features. So why basically we want to reduce the number of features? What are the benefits of it? So that all is basically written here, that why we want to reduce the number of dimensions. So the many machine learning algorithms work better if the dimensionality, means the number of attributes in the data, is lower. So if the number of dimensions or the number of features are lower, so a lot of algorithms work better. Why it is so? We will just see. This is because the dimensionality reduction can eliminate the irrelevant features and reduce noise and the curse of the dimensionality. So obviously some of you must be thinking of that, if suppose we go for a lesser number of dimensions or a lesser fewer features, then why we will get the better result? Because usually what we think is the more is better. But actually it is not always so that the more is better, especially in case of the machine learning algorithm, where the number of features are too huge. It will be a problematic for the algorithms, and rather we would like to reduce the number of dimensions. So here the more is rather not better. But I never mean to say that in case of the data analysis, always lesser is better. It is not so that you should generalize it in a complete sense. Okay. uh, and why it is better? In most of the cases it is better just simply because we have the irrelevant and the redundant features, as well as the noise also. So if we remove the redundant or irrelevant features, then the noise will be removed. And the other important part is basically the curse of dimensionality that we will discuss in the next slide, that what is the curse of dimensionality. So what we see, the first point is, the first point simply says that a lot of benefits are obtained by the dimensional reduction. And the first benefit is that the lesser is better, not the more is better. And why it is so? Because few of the things are irrelevant. Okay. Few of the things means few of the features are irrelevant. The second is that it can lead to more understandable model, because the model may involve the fewer attributes. Attributes are nothing but basically the features. Okay, so attribute, dimension, feature, they all are basically synonym to each other. So definitely if we have a lesser number of features, then we will be able to understand the model, or we will be able to comprehend the model in a more better way, because it will be having a lesser number of features. So for example, if I go for the rule base, so classifier which are based on the rule basis, so the number of features will be lesser. So if this and this and this, then it belongs to this class. So if and lot of every few ends will be there, then it will be very easy for me to understand that, okay, if this is this, then it belongs to this class, in comparison to the other one, where that if this feature value is this, and this feature is value this, and this feature is value this, and this feature is value this, and lot of ends are there, and then it belongs to this class, then it will be very difficult for me to comprehend or the understand. So the more lesser the features are, the more better will be, or more comprehensible the models will be for the human beings. I mean, they will be able to understand in a more better way. The third is that it may allow easy data visualization. And if you remember, I told you that the data visualization is also a one aspect which we use heavily to analyze the data. So obviously the data visualization will be easy if we have a lesser number of features. So why it will be easy to visualize if we have the lesser number of features? The simple reason is that it is written here in the next sentence, that even if the dimensionality reduction does not reduce the data to 2 or 3 dimensions, data is often visualized by looking at pairs or the triplets of the attributes, and the number of such combinations is greatly reduced. What it simply says, the sentence may be a longer one, but it simply says that if suppose I have a 2 dimensions, only xy plane, a plane is there, okay, then I can put anything as a point. I know that when I say I means we all know, and it is very easy to understand something if it is in a 2D plane. So we can comprehend it very easily. If suppose a one more dimension is added to it, and if we have the x, y, z, the 3 dimensions, so there also we can understand very easily, because we have studied the 2 dimensions and 3 dimensions images, graphs, figures in a much detail, even in class, smaller classes, I mean lower classes also. So we all can understand very easily. But suppose if we have the dimensions more than 4, it becomes very difficult for the human beings that they can understand it in a nice way. And we say that whenever we are going for the reduction of a feature, it does not mean that the features will be reduced to only the 2 features or the 3 features. Even then, how the visualization will be easy? It will be easy for the simple reason, because if you remember about the uh, visualization of the features, so what we do is that, for example, if I take the scatter plot or the scatter matrix, so in case of a scatter plot, what we have, we basically have the 2 dimensions only. It means only the 2 variables or the 2 features are taken, they're plot into the xy, and we see that what is the correlation between the two attributes. If we go for the scatter matrix, so what is there? If suppose a more number of dimensions are there, so it creates basically a matrix. If suppose n number of features are there, so it will create basically n into n square matrix, where the relationship between all the pair of the dimensions can be understood very easily. So what we do is that we either go for example, if we go for the scatter matrix, so if the n is reduced, Okay, suppose n was earlier, now it is reduced to say half only. So instead of n into n matrix, you will get basically n by 2 into n by 2 matrix. So how less number of graphs will be there, so how easy it will be for you to understand. So the simple meaning is that basically most of the visualization techniques, if the number of features are lesser, they becomes more better for the visualization by the human beings. So the lesser the features we will have, the better it will be. The fourth one is the amount and time, the amount of time and memory required by the machine learning algorithm is reduced with the reduction in dimensionality. So this basically simply tells that suppose if we have a lesser number of features, so the time that we will take to compute and the memory that we will require to store the data, it means the space complexity and the time complexity of the algorithm will be lower in comparison to the earlier one. So what we see that if we go basically for the dimensionality reduction, then a lot of benefits are there. So definitely we have a point that we should go for the dimensionality reduction. So the term dimensionality reduction is often reserved for those techniques that reduce the dimensionality of a data set by creating new attributes that are a combination of old attributes. So if you remember what we discussed, the feature selection and the feature extraction. So simply what is written here is that though I have written here the dimensional reduction, so I am talking of in a general sense as a dimensional reduction, and the this paragraph simply I have written just so that the few books, they say that the dimensional reduction means basically the feature extraction. So here in this case, I am using the dimensionality reduction in a general sense and not only as a feature extraction. Because if you remember what we discussed in the feature extraction, we said, I told you that we basically combine the features by using the mathematical models so that the features are basically reduced. Okay. So that is the feature extraction, and that is what the few books write as a dimensionality reduction. But here, when I say dimensionality reduction, means in a general sense. The reduction of dimensionality by selecting the new attributes that are a subset of the old is known as a feature subset selection or the feature selection that we have discussed earlier also. Now we just discuss what is basically the curse of dimensionality and why we are discussing it. So the curse of dimensionality, the meaning is basically very simple. As the name indicates, the curse of dimensionality, that if the dimensionality is too huge, it's basically a curse. Okay. So the curse of dimensionality refers to the phenomena that many types of data analysis becomes significantly harder as the dimensionality of the data increases. So why we consider a large number of dimensions as a curse? Okay, so that is written basically here in the next sentence. Obviously this sentence defines it, that when the number of dimensions are too huge, then it becomes very harder for some of the algorithms to analyze the data. So now it is very clear that if a large number of features are there, then few algorithms find it very difficult to analyze the data in case of a number of features are too huge. Specifically, as dimensionality increases, the data becomes increasingly sparse in the space that it occupies. And I do not have a figure right now here, and it's my mistake. I have a figure, I should have included it here in the next slide. I just forget it. What basically is known, it can be represented very easily by an image. And what is the meaning of a second sentence is that as the dimensions increases, the data set loses its meaning. When we say as the dimensionality increases, the data set loses its meaning, and the simple reason that why it loses its meaning is that it becomes basically the sparse. And the meaning of this is that almost all the data is basically at the equidistance. I simply mean to say that if suppose you have the two attributes only, suppose X and Y, and the two data objects will be the X1, Y1 and X2, Y2. And suppose if there is a one algorithm which says, which takes the difference of the objects. And suppose the distance is being used as a difference of the object. So I will find, for example, the Euclidean distance. So under root x1 minus x2 square plus y1 minus y2 square. If suppose I have the 3 dimensions, okay, so x, y, z, you see that what will be the values? I mean, computed value, the distance value. Okay, just go on, take a variety of the data set where the features are increasing. I mean, the dimensions are increasing. So you will just find that after the certain number of features, I mean, X, Y, Z, A, B, C, when the number of features increases too much, then after that, whatever the two objects you will take, you will find that almost all the object distance between the two objects are almost very similar to each other. That is what is the meaning when I say that the large dimensionality, in case of a large dimensionality, the data loses its meaning. And why it is important? It is important because either you go for the supervised learning or you go for the unsupervised learning. A lot of algorithms are there which basically works on the similarity and the dissimilarity measure, or they may be using the density of the data objects or so. So if suppose you are trying to find out the density or the similarity or the dissimilarity on the basis of the distances, and if the number of dimensions are too huge, everything is almost equidistance. So it is as good as a random sampling or a random type of thing. Okay. So in case of a random type of thing, you won't be able to learn anything. For the learning, there must be some pattern. And when we say that we are learning means what basically we are learning? We are learning basically some pattern which is in the data. So whether it's basically a machine learning or whether it's a data mining, what we do is basically in case of the machine learning also, suppose I'm going for the classification. So what I do, I just try to learn basically a pattern that if the data follows this particular pattern, it belongs to this class. If the data follow some other pattern, it belongs to the other class. So there also basically what we try to do is we try to basically learn the patterns, what the different patterns are. And obviously, if everything is something like a completely random, then we will not be able to find any pattern in that. So that is why if suppose the number of that is why if the number of dimensions are too large, a lot of algorithms we will not be able to implement on those data sets. Okay, so because of this, we need to reduce the dimensions, and because of a very huge number of features, the everything becomes almost random. So that is basically the curse of dimensionality. So the second particular paragraph makes it more clear what I just told you, that for classification, this can mean that there are not enough data objects to allow the creation of a model that reliably assigns a class to all possible objects. Why? Because they all are almost equidistant. So it will be very difficult to assign that what is the similarity or what is the difference among the objects, and how to define that it will belong to this class or that class. So that is basically a classification is the supervised learning. So in supervised learning, this is a problem. For clustering, so clustering is basically a unsupervised learning. So for clustering, the definitions of the density and the distance between points which are critical for the clustering becomes less meaningful, means because everything is equal distance. So there is no meaning of a distance, there is no meaning of a density, etc. So again, it will be basically useless. So whether we go for the unsupervised models or we go for the supervised models, it becomes very difficult that we find anything here. So that is why that is known as a curse of dimensionality. And various ways are there to reduce the dimensions. I mean the feature extraction, and that is the principal component analysis and the singular value decomposition are the most common for the dimensional reduction in the continuous data. And this we are talking of a feature extraction, not the feature selection. Okay, and they use the linear algebra to project the data from a high dimensional space into a lower dimensional space by using the mathematical functions as it is written here, the linear algebra. So these are some complex methods. We do not have the time to discuss all these things. So we just come to basically the feature selection. Okay, so another way to reduce the dimensionality is to use only a subset of a feature. It may seem that such an approach will lose the information, but this is not the case if the redundant and irrelevant features are present. So some of you obviously may think of that we are removing few of the features. So if we are removing few of the features means we are corrupting the data. Actually, we were discussing that we have to make the data more pure, but some of you may think by eliminating or by reducing, by eliminating few of the features, we actually are corrupting the data, but actually it is not so. Why it is not so? For a very simple reason that a lot of features may be redundant or that may be relevant. Now, what is the meaning of a redundant feature or the irrelevant features? So the redundant features are basically that duplicate much or all of the information contained in one or more other attribute. As the name itself indicates, a redundant feature means whatever is the input which is hidden in this particular feature, or whatever this information, this feature is giving me the information that is already available in some other feature or other features, either fully or partly. So in that case, this feature obviously may be termed as a redundant because this information is already available. So I can remove this feature very easily. The irrelevant features. What are these irrelevant features? The irrelevant features contain almost no useful information for the machine learning task at hand. So you need to emphasize this particular word, for the machine learning task at hand. So I don't say that if a one particular feature is irrelevant for my particular task, it means that that particular feature is irrelevant for all the tasks. Okay, that is the meaning of this particular sentence, for the machine learning task at hand. Because if that particular feature is irrelevant for each and everything, then why unnecessary it is there into the data set? Obviously, I will eliminate it completely, but actually it is not so. What does it mean? That if I'm interested in task A, so maybe this feature, and this feature is irrelevant. If suppose someone else is looking for the task B, then some of these features which for me which are irrelevant may be relevant to him, and some other features which are relevant to me may be irrelevant to the other person. So the simple meaning is, so other person means the other task actually. So the basically the irrelevancy of the feature is dependent on the task. So that is why we cannot say that these features are irrelevant and remove them altogether. So we need to find out the redundant features and the irrelevant features. And if in our case, there are few irrelevant and the redundant features, we can just simply eliminate them. And obviously in that case, we will get basically the reduced feature set. And that is what basically we need to do. So such features can reduce the classification accuracy and the quality of the result. So the one thing is that it will reduce the computational complexity and the time complexity. That is the one aspect. And the other more important aspect is that the such features, such means the irrelevant and the redundant features, they can reduce the classification accuracy and the quality of the, it is written here, the clusters. You please read it as the quality of algorithm. Okay. Quality of any algorithm what is at hand. So what will happen is that the irrelevant and the redundant feature not only hinders the algorithm, but rather they deteriorate the accuracy also. Means if those features are present, then the algorithm will give the bad result. If those algorithms are not present, the algorithm will give rather the good or the better results. While some of these attributes can be eliminated immediately by using common sense or domain knowledge, selecting the best subset of features frequently requires a systematic approach. So what is written here is that suppose if the number of dimensions are not too huge, and if you have a good domain knowledge, and if you have some statistical tools a little bit, so you can just apply them, or you can just go for the visualization tools. So you can just go for the visualization, or if you have a domain knowledge, so you can guess that okay, this may be irrelevant, this may be relevant, this may be redundant, and you can just go on. But definitely if you are not an expert, you are not having a domain knowledge, and if the number data set is unknown to you and the number of features are too huge, then obviously you cannot do that. It means the gut feeling can work in very few limited cases, but the gut feeling or the domain knowledge cannot work in all the cases where the complexity of the data set is basically more. So there we need to have basically not an ad hoc approaches, but rather the systematic approaches. The systematic approaches means some mathematical tools, models that will be applied on the data set to find out that what is relevant, what is not, and what is to be removed and what is not to be removed. The ideal approach of the feature selection is to try all possible subsets of the features as input to the machine learning algorithm and then take the subset that produces the best results. This method has the advantage of reflecting the objective and bias of the machine learning algorithm that will eventually be used. So what is written here is that suppose if we have to go for the feature selection, so obviously the best strategy is that you go for each and every subset that is possible, and then you see that for what particular subset your algorithm is giving the best result, and then you say that this subset is basically the best one. But definitely there is no meaning of it, because it is written here in the next sentence, unfortunately, since the number of subsets involving n attributes is 2 to the power n, such an approach is impractical in most situations and alternative strategies are needed. There are three standard approaches of the feature selection, that is embedded, filter, and the wrapper. So what we discuss here is that why it is, I mean, this approach, that is exhaustive approach, why the exhaustive approach is not advisable. Exhaustive approach is not advisable because for the n number of attributes, there are 2 to the power n possible subsets, and you remove the two subsets out of it. Obviously, why? Because the one subset will consist of the null set, that no feature is there. So obviously there is no meaning of it. And the other subset will be basically the same set. I mean, there is no reduction. So all the n attributes or the n feature will be there. So definitely eliminate that also. So total 2 to the power n minus 2 subsets will be there. So even that is also a too large number. So there is no meaning that we will go for computation, so large a computation, and then we will see that which is good and I mean which subset is good, which subset is not bad. So this approach is basically not practical. So what is practical? So for that we have the embedded, filter, and the wrapper approach. Now we see that what these approaches are. The embedded approach is that the feature selection occurs naturally as part of the machine learning algorithm. So what is the meaning of this? In case of the embedded methods, actually the feature selection is embedded into the machine learning algorithm. It means we do not tell that what is to be done. The machine learning decides on its own that what is to be done, means which features has to be removed and which features are to be kept basically for the making of a model. Specifically, during the operation of the machine learning algorithm, the algorithm itself decides which attributes to use and which to ignore. So obviously you can think of that this is obviously the best approach, that give the whole data set, I mean the full feature set to the algorithm, and the algorithm will itself decide that which is relevant, which is not relevant, and it will work on its own. So it doesn't require any human intervention. Okay, so the important part, I will just discuss about the wrapper. I will compare the wrapper and embedded. So that is why I'm emphasizing this point, that in case of the embedded, we do not tell what is to be done. The machine learning algorithm does on its own. The another one is the filter approach. What is the filter approach? Features are selected before the machine learning algorithm is run using some approach that is independent of the machine learning task. For example, we might select sets of the attributes whose pairwise correlation is as low as possible. So the first point is an up to, and that is to even up to this comma. I mean, half of the sentence is very important. The features are selected before the machine learning is run. It means here the machine learning algorithm is not a part of the selection of the features. Rather, the selection of the feature is independent of the machine learning. It means we are not going to use any machine learning algorithm for finding out that which is important, which is not important. Whether it will be done separately. So what we will do, we will use basically some statistical or some other models to define that what is relevant, what is not, and then we will take a reduced feature and we will give it to the algorithm. That is basically the filter approach. What is the wrapper approach? These methods use the target machine learning algorithm as a black box to find the best subset of the attributes, but typically without enumerating all possible subsets. And in case of the wrapper approach also, what happens? The machine learning algorithm is a part of finding out that what is basically the what is the reduced feature set. Okay, so in case of a wrapper approach also and the embedded approach also, we use basically the machine learning algorithm to find out the reduced feature set. In case of the filter approach, we do not use the machine learning algorithm, but rather the irrelevancy of the features are selected in advance. Okay. And in case of the wrapper method, the machine learning is basically used as a black box. It is used as a black box means what we simply do is that we give basically a one subset to the machine learning algorithm. It will find it out what is the output. Then the other subset will be given to it. It will find what is the output. So by taking a lot of different subsets, machine will say that, okay, I mean, the learning algorithm will say that obviously because we will have the output. So by analyzing the output, we will come to know that which output is more better. So for whatever the subset, the output is better. We will say that, yes, this subset is a more appropriate for this particular task. So basic, but obviously here also, it is not so that we will enumerate all the possible subsets. Enumerate all the possible subsets means exhaustive search. But obviously, if we are going for the exhaustive search, then there is no meaning of it. So what we do in case of the wrapper approach is that instead of going for all the possible subsets, we give basically few selected subsets to it. And from those selected subsets, we try to find out which is the better one. So obviously, in a very lesser time, we are able to get basically the good feature set. Okay, so these three approaches are very common. That is the embedded approach, the filter approach, and the wrapper approach. Okay, so what is written here is that an architecture for the feature subset selection. It is possible to encompass both the filter and the wrapper approach within a common architecture. So we say the wrapper and the filter means these two can be thought of or can be explained in a very better way using a one architecture. Okay, a common architecture. What that common architecture will have, that feature the feature selection process is viewed as a consisting of four parts. So that common architecture will have these four parts. The first one is a measure of evaluating a subset. Okay, obviously we have the lot of subsets, so we need to find out that which subset is good, which subset is bad. So obviously there must be some method by which we will be able to say this is good, this is bad. So that is a very normal thing, a measure or a method by which we will evaluate a subset. The second is a strategy that controls the generation of a new subset of the features. Definitely, we have to create a subsets. Okay, only then we will just try to see that which subset is good or bad. So what should be the method for generation of a subset? Obviously, it is not so that we are going basically for the exhaustive search. Okay, it is not possible. We have already discussed it. So there must be some good methodology which will tell us that what may be a good next good subset. Okay, so there must be a some way by which we will be able to define what is the subset, because we do not want to go for the exhaustive search of the subsets. Okay, the third one is a stopping criteria. Why? Because we are going for the creation of a subset, test this subset, then the other subset, then the other subset. In this way, if we go on, ultimately, if we do not stop anywhere, we will go for the exhaustive search. By ultimately one by one, we will make all the subsets and we will test all the subsets. So definitely we must know that where to stop. We will say that, okay, we have done enough work and now stop it, and whatever the best subset is there, that is okay and done. So there must be some stopping criteria also. And then at the last, we have a validation procedure. So whatever the subset we have find it out, obviously there must be some way that will tell us that, yes, this subset is basically the better one. So these four are the must things in the architecture. Okay. Filter methods and the wrapper methods differ only. We will take the architecture, so don't worry. In the next slide, it is there. The filter methods and the wrapper methods differ only in the way in which they evaluate the subset of a feature. Okay, this is important. What is, sorry, what is written here? They differ only in the way they evaluate the subset of a feature, means how to evaluate the feature. I mean, the first criteria which is written here. So that is the only difference. And why it is very clear. If you remember, I told you that in case of the filter method, we do not use the algorithm. I mean, the data mining or the machine learning algorithm. In case of the wrapper method, we use the machine learning algorithm. So in one case, we do not use the machine learning. In the other case, we use the machine learning. That is the only point where it differs. Otherwise, both the processes are very similar to each other. For a wrapper method that is written in this sentence, for a wrapper method, the subset selection evaluation uses the target machine learning algorithm, while for a filter approach, the evaluation technique is distinct from the target machine learning algorithm. That is what I just told you. Conceptually, the feature subset selection is a search over all possible subsets of the features. Many different types of search strategies can be used, but the search strategy should be computationally inexpensive and should find optimal or near optimal sets of the features. It is usually not possible to satisfy both the requirements, and thus the trade-offs are necessary. What basically this paragraph tells you? This paragraph suggests you that we can view this feature subset selection as an optimization problem. Why optimization problem? Because if I say that this is basically a search space, okay, in this search space, a lot of subsets are there. Out of these lot of subsets, it depends on the n. If n is large, then the search space may consist of the millions of the subsets. So millions of the different answers are there, and each subset is basically an answer. So million of the answers are there. Out of the million of the answer, one answer is basically appropriate. Appropriate, I mean to say, that is basically the optimum one. So what is this? This is basically a optimization problem, that among a lot of solutions, I have to find out the most optimal solution. So definitely it's an optimal solution. Sorry, it's an optimization problem. But what is the other thing? Suppose if we go on searching a lot, then algorithm will be very much expensive. So algorithm should not be very expensive. So that is a one objective. So my one objective is that whatever the algorithm I will use, it should not be very much expensive. Expensive mean to say that time complexity, space complexity, etc. And the other one is that it should find the optimal or the near optimal solution. That is basically the second objective. So we have the two objective. If suppose I go for a most optimal solution, then obviously the algorithm will become much computationally expensive. If I go for the less computationally expensive algorithm, then I may not be able to find the optimal solution. So if I try to achieve this, this will go away. If I try to achieve this will go away. It means that there are two different objectives. So it's basically a bi-objective, means the multi-objective problem. So in case of a multi-objective problem, basically we have to find it out that what is the trade-off of the two objectives. So we need to find out the trade-off. So basically we can view the feature selection problem as a trade-off of a multi-objective problem, where the two objectives are that the solution must be the optimal one and the algorithm must be inexpensive. Okay. Now we come to the process common architecture that we were discussing here, that we have basically a one common architecture. And what is that? You see that here we have the attributes. So the attributes means the full set, all the what is the input data set which is given to me. So that is the full feature set. So you say that it is basically the full feature set. Okay. What will happen? This full feature set will basically go to the search strategy. What is this search strategy? The job of this search strategy is basically to generate the subsets, okay, of the features. That is basically this one, a search strategy that controls the generation of a new subsets of the feature. So what is written here as the second one? So this is basically this, that attributes will be given as an input to the search strategy. What the search strategy will do? The search strategy will generate basically a subset. Okay. This subset, this is the output of this process. So this output of this process is basically an input of this process. What is to be done? This subset will be basically evaluated, that whether this subset is good or bad. And here basically the evaluation criteria is different. That is basically this first one, a measure for evaluating the subset. So this is basically a measure for evaluation of a subset. So here in case of the wrapper, we will have the data mining or the machine learning algorithm. And in case of a filter approach, it will be some statistical or some other tool that will find out that whether this subset is good or bad. Okay, so this will be evaluated here. Then we will go to the stopping criteria. As I told you that if the stopping criteria is not there, we will just simply go on enumerating the different attributes, subsets, and we will go for the exhaustive search. So definitely we need to see whether we have to stop or not. If suppose we do not have to stop, we have not, stopping criteria doesn't satisfy, then I mean not done, then come here, generate a next subset and then test it. So unless the stopping criteria is satisfied, go on generating basically a lot of subsets and evaluate them that whether they are good or bad. So when the stopping criteria is satisfied, so it means we know that what is basically the attribute subset, which is good. So just take that attribute subset. So that is basically the selected attributes. So the selected attributes will be taken. And for those selected attributes, we will go basically for the validation procedure, that whether that particular subset feature subset is really good or not. And that is basically the fourth one, and that is basically the validation procedure. Okay. So what is written here, that we can view the filter or the wrapper approach as basically a one as a process. So that is written here, that how we can view it as a process. And the only thing is that this point is basically different in both the cases. Okay. Now we will just take each one by one. So search strategy. So the basic heuristic methods of attribute subset selections are as follows. So what are that? And obviously, because we say that we have to find out the different subsets. Okay. And we say that we will not go for the exhaustive search. So what we will do? We will have to use basically some heuristics. I think you all know what is the meaning of a heuristic. Okay. So we will use basically some heuristics. So that heuristics will tell us that what is basically the next good subset that is to be tried. Okay. So we just see here few. It is not basically an exhaustive list. These are just few examples here. A stepwise forward selection. So the procedure starts with an empty set of the attributes as the reduced set. The best of the original attributes is determined and added to the reduced set. At each subsequent iteration or step, the best of the remaining original attribute is added to the set. So what is written here and what the stepwise forward selection does, as the name indicates, it basically starts with a null set, nothing is there. And then each time one by one, one attribute is added into this empty set. Okay. How it will be added? We will see that which is the best attribute. So there must be some way to find out that which is the best attribute now. And in this way, it will be added. And unless the stopping criteria is satisfied, we will just go on doing it. And once whatever the output is best, we will take that as a final one. The other one is the stepwise backward elimination. It is just opposite of the first one. I mean the stepwise forward selection. And what it does, it starts basically with the full set and it eliminates one by one the least fit, then the second least fit, and the so on. And it will go on till the best output, I mean the best feature set is basically obtained. The next one is the combination of a forward selection and the backward elimination. What it does, as it is written here, that the both things will be applied simultaneously. So it will one least good feature, least best feature will be eliminated, and the best feature which was not there earlier, it will be added into the set. So the stepwise forward selection and the backward elimination methods can be combined so that at each step, the procedure selects the best attribute and removes the worst from among the remaining attributes. So this is how it works. And then the decision tree. So we know that the decision tree, if you know, the decision tree is basically a classification algorithm, and what it does with the given features, it gives us basically a tree, and that tree consists of the features, that if this feature value is this, then this feature is value this, then this feature is value is this, then it belongs to this class. So what it does, it basically tries to find out in this way when the tree is completed. After that, when the tree is completed, you will get basically the features in the tree. The internal nodes will be basically the features, and these features are basically the relevant features. All other features are redundant or the irrelevant feature. Okay, and that is what basically we have to do. So we can use the decision tree, that is a classification algorithm, also as basically a feature selection algorithm. So that is written here. The decision tree algorithm were originally intended for the classification. When decision tree induction is used for attribute subset selection, a tree is constructed from the given data. All the attributes that do not appear in the tree are assumed to be irrelevant, and the set of the attributes appearing in the tree from the reduced subset makes basically the reduced subset of the attributes. So let us take it by an example. It will be more clear. I know by language the things are not that clear, so I have taken this figure. So suppose if the initial attribute set consists of the A1, A2, A3, A4, A5, A6, six attributes were there. So what will do the forward selection? It will start basically with the empty set. I mean, no attribute is there. And then it will see that which attribute is the best one. So among this, the A1 attribute is the best one. So A1 will be considered. Okay. And then we will evaluate that whether this, what is the quality of this attribute subset. Then after that, the next best, suppose the next best is basically the A4. So the A4 will be added. So the A1 and A4. Now this is another subset. So this subset will be evaluated whether this subset is good or bad. After that, next third best feature will be added, and that is, for example, the A6. So the A6 is added here. So the A1, A4, A6. So this is the another subset. So in this way, it will just go on. In this example, we have stopped here only. Okay. So this is how basically the forward selection goes on. And the backward elimination is just opposite of it. And what it will do, it will start basically with the full feature set, 1, 2, 3, 4, 5, 6. Then in the next step, what it will do, it will eliminate the one feature which is the worst one. So in this example, you see that the A3 has been eliminated. The 1, 4, 5, 6 is here. So A3 was basically the worst feature. So it has been eliminated. So this is another subset. We will just test it that whether this is good or bad. After that, we see that the A5 is the another worst subset after the A3. So in the next step, the A5 will be eliminated, and then the leftover will be the A1, A4, A6. So this will be done, and so on. So this is how the forward selection goes. This is how the backward selection goes. In case of the combination of a forward backward, suppose if it is the A3, A4, A5, for example, if this is the case, so what it will do, it will just eliminate the one which is the worst from here. So suppose the A5 is the worst, so A5 is eliminated, and whatever the leftover is basically the A1 and the A6. So the A1 is basically the best one, so A1 will be basically introduced. So among the A3, A4, A5, the A5 will be eliminated and the A1 will come. So now the next subset will be basically the A1, A3, A4. So one worst from the set will be eliminated, and the best among the remaining will be basically introduced. Okay, so that is the combination of the two. In case of a decision tree, what happens? Suppose if this is a decision tree, suppose it's a binary problem. I mean, the only two classes are there, binary classification problem. So we made a decision tree, and this is the decision tree, that if the attribute value of the 4 is this and the attribute value of 1 is this, then it belongs to class 1. If this is yes, this is no, it belongs to class 2, and so on. So here we got that the A4, A1, and the A6, that is basically the irrelevant features for this task at hand. So the subset feature which is found is the A1, A4, A6. This is how basically the search strategies we can just think of. Okay. And again, I told you that in the different books, you may find the different other methods also. And there's, I don't claim that I'm going basically for the exhaustive methods. Then we exhaustive search of the methods. Evaluation strategy. Then the next step is basically the evaluation strategy, that how to evaluate that whether this subset is basically really good or not. So an integral part of the search is an evaluation step to judge how the current subset of the features compare to the others that have been considered. So definitely we have taken a few subsets. So among the few subsets, which subset is better? So obviously it is an integral part of this process. So this requires an evaluation measure that attempts to determine the goodness of a subset of attributes with respect to a particular machine learning task, such as the classification or the clustering. So whatever the task that we are into, either the classification or clustering, so as per that classification or clustering algorithm, what is the quality of this particular subset? Okay. As I told you earlier also, that in case of the filter and the wrapper approach, this particular strategy is completely different. So that same thing is written here, that for the filter approach, such measures attempt to predict how well the actual machine learning algorithm will perform on the given set of attribute. What it does, such measures attempt to predict how well it will do without using the algorithm. So it doesn't use the algorithm, it uses some statistical or some other mathematical tools to find out that what is the goodness or the quality of the particular subset. In case of the wrapper approach, where the evaluation consists of actually running the target machine learning application, the subset evaluation function is simply the criteria normally used to measure the result of the machine learning algorithm. And here we say that the machine learning algorithm itself is basically a part of the evaluation strategy. So what we will say, if the classification accuracy is good, or say for example, if it's a clustering problem, if the clustering results are good, then we will say that obviously this subset is better. So whatever is the goodness criteria of the machine learning at hand, I mean the task machine learning task at hand, the classification, clustering, outlier detection, whatever it is. So on that performance, we can say that what is good or what is bad. I mean, what subset is good or what subset is basically bad. So the same thing which we discussed earlier is written here. Then we talk of a stopping criteria, that what will be the stopping criteria when we will go stopping. Because if you do not stop, we will go on enumeration or the exhaustive search. So this strategy is usually based on one or more conditions involving the following. So we say that either we can take any of this or we can take any combination of this. And again, here I say that this is not an exhaustive search. If you go on different books or if you search on the net, you may find a lot of other stopping criteria also. And you can go any sort of the mix and match of these methods for the stopping criteria. The number of iterations, maybe suppose if I say that I will go for the 50 number of subsets, and among those 50, whatever is the best one, I will take it. It doesn't matter that is the best or that is far away from the best, but I am exhaustive in the 50 search iterations. 50 iteration is my limit. So it means the number of iterations may be a one stopping criteria. In the same way, whether the value of the subset evaluation measure is optimal or exceeds a certain threshold. Other is that we may just take basically that if suppose for example, if I say that my classification or the clustering or algorithms accuracy is say for example more than 95%, so I am happy with it. So I will just go on computing, and as soon as I will see that for this particular feature subset the accuracy of my algorithm goes beyond 95%, I will be very happy. I will say simply stop, this is the final subset for me. Maybe if I go for some other subset, probably I may find a subset that will give me the accuracy of 98, 99, but my threshold is 95. I am happy, so it's done. So the threshold may be basically a one criteria. Exactly in the same way, whether a subset of a certain size has been obtained. A certain size means that I suppose I do not want to have more than 10 attributes. So the moment I reach the 10 attributes, I will simply stop. And among this, whatever is the among this means there will be some sets of the attribute one, some subset will be of the attribute two, some will be of three, and so on. So among these, whichever is the best one, I will take that as a final one. Then whether the simultaneous size and the evaluation criteria has been achieved, we can take a combination of a size and the evaluation criteria, that whether the threshold has been taken or the iterations has been taken, something like this. Or whether any improvement can be achieved by the options available to the search strategy, that if I'm going for the more computation, so whether the algorithm's accuracy is increasing or not, so that also I can take. So different type of the stopping criteria can be basically thought of, and we can think of combinations of these also. Then we come to the validation. So in case of validation, finally, once a subset of the features has been selected, the result of the target machine learning algorithm on the selected subset has to be validated. Definitely, whatever the machine learning algorithm we have for which we are finding out the subset, obviously we need to test the subset on that particular algorithm. So if on that algorithm it is giving me the good result, the job is good. Otherwise, I have done a bad job. So that is basically the validation, that whatever the feature subset that we have selected, whether it really gives the good result on the algorithm for which I have to use it. A straightforward evaluation approach is to run the algorithm with the full set of the features and compare the full results to the results obtained using the subset of a feature. So here what I say, that you run on the full subset and then you run on the full subset means basically the full set actually on the n number of features, and then you have taken the m number of features subset, run it on that subset and see that where the results are good. Then definitely some of you may think, sir, you were discussing since long that we have to find the subset, and now you say that you run the algorithm on the full set and on the subset to check whether this is really good or bad. Now what is a joke, whether this is a joke? Because if I'm running it on the full subset, then what I'm doing, I'm running on the full subset and then I'm running on the small subset. So why run on the small subset? I have already run it on the full subset, so my job is done. So again, the thing is that actually, if you remember, I told you that uh, few of the attributes may be irrelevant, few of the attributes may be redundant. So if you run on the full subset, the accuracy may be worse in comparison to the subset. So whenever we say that you run it on the full and the subset, so it's not basically a joke, it's really basically a valid point. Okay. But the other thing is, hopefully the subsets of the feature will produce the results that are better than or almost as good as those produced when using all the features. So in most of the cases, you will find if the number of features are really too large, because the few will be irrelevant and the redundant, that the subset result will be better in comparison to the full set result. So that is why this comparison is basically meaningful. It is not meaningless. But definitely a better approach is also there, and that is written here in the next sentence or next paragraph. Another validation approach is to use a number of different feature selection algorithms to obtain the subsets of the features and then compare the results of running the machine learning algorithm on each subset. So here what we say, that you use basically a different variety of the feature subset selection algorithm. Do not depend on a one feature subset selection algorithm. Rather, you rely on the, or rather you take a different variety of the subset selection algorithms. So obviously, because we are taking a variety, so they will take, they will give you the different feature subsets. So you run your algorithm on those different feature subsets and then see for which it is better one. So if suppose your original feature set is too huge and the reduced feature sets are too small, or rather much smaller than the full set, then it makes sense that instead of taking the full set and the small set, you run basically on the small subsets only and you see that which one is better. So obviously someone will be better because you will have a lot of different subsets that has come from the different variety of the algorithms. And different variety of the algorithms, when I say for the feature substitution, means their working philosophy will be different. So because of that, their features produced feature subsets also will be basically different. So there will be a really good variety into the feature subsets. So that is why if your algorithm is working good on some of the feature subsets selected in this way, so that will be really good. That is what I mean to say. Then we come to the other aspect, and that is basically the feature weighting. So this feature weighting is a alternate of the feature reduction. And when I say it is an alternate of the feature reduction, what does it mean? Here in this particular process, we are not going to eliminate the features completely. I mean, suppose I'm not going to make the M number, I'm not trying to find out the subset of feature set. Rather, I will take the full feature set. But what I will do is that in this full feature set, I will give basically the weights to the attributes or weights to the dimensions. Attributes means dimensions, whatever you call that. So a few of the attributes will have the more weight and the few of the attributes will have the lesser weight. So obviously the next question should be that if I have to assign the weights, the few will get more and few will get less. So how to do that? And what is the way and why to do that? Why to do that, and what is the way to do that? So why we do that? For the simple reason is that the one which is having which is where the uh, uh, not partial differential, uh, where the variability is more, okay, where the variability is more, when I say the variability is more, it simply means to say that which is a more distinguishing feature among the classes or the clusters, okay. Because maybe some, for example, if I take for example the loan processing by the bank, okay, so a lot of features may be there, the age and say income, and whether the person is married or not, I mean marital status, and some other features may be there. So, here in this particular example, obviously if I take these three features only, so the monthly income is basically most important for the bank, because if the monthly income of the person is more, then he will be able to repay the loan, so he is a better person to give the loan. Age obviously matters, but it doesn't matter too much, okay. And marital status also doesn't matter too much as the income matches. So what we will do here, the monthly income basically is more important, so we will give more weight to it. So what I simply mean to say is that the feature weighting is that we find out that which particular feature is more important for the problem, and the weight is assigned accordingly. So the more important, more weight, less important, less weight. Okay, so that is given here. The more important features are assigned a higher weight, while the less important features are assigned a lower weight. These weights are sometimes assigned based on the domain knowledge about the relative importance of the features. If suppose I have a domain knowledge, like the example which I gave you, that marital status, income, and the age. So it's such a simple example that I can say that I have a domain knowledge. So on the basis of the common sense or the domain knowledge, I told you that the income is more important. Okay. So if the person is having a good domain knowledge from where the data set has come, so he or she will be able to distinguish that which feature is more important, which is less important. Accordingly, the weights can be assigned. Alternatively, they may be determined automatically, means the algorithm will do on its own. For example, some classification schemes, such as the support vector machine, produces the classification models in which each feature is given a weight. So what is written here is that if you have a domain knowledge, you can do it on your own. If it is not so, then it can be done automatically also. Automatically means the algorithm will do. And then it is a support vector machine is basically a one classification algorithm. And it is taken here as an example only, that the support vector machine is a one example of a machine learning which produces a model where the weights are assigned to the attributes, and the weights are assigned basically on the basis of the data set by the algorithm on its own. We do not say from our side that what will be the weight of this. Okay, so it means that this is basically an example where the weights are assigned automatically. The features with the higher weights play a more important role in the model. So that is normal sentence. There's no need to say. Obviously, the more weights are there, they are more important features, so they will play more important role. Usually it is possible. Now we have come out of the feature selection. So feature selection part is done. Now I am coming basically to the feature extraction. Okay, feature extraction means where we will create the new features from the features which are already present, and then we will remove the features. Suppose the three features are mixed into a one feature, so these three features will go away and the new feature will be will become a part of it. So the total number will become n-2, because 3 has gone, 1 has come, so the total is n-2. So usually it is possible to create a new set of reduced attributes from the original attributes that captures the important information in a data set much more effectively. It allows us to reap all the previously described benefits of the dimensional reduction. The three popular methodologies for creating the new attributes are, the feature extraction, mapping the data to a new space, and the feature construction. So what we do basically in the feature extraction, the feature creation of a new set of features from the original raw data is known as a feature extraction. So what is the feature extraction that is given here? In some cases, what happens is that the feature is not known to us, but we have been given a raw data, and from that raw data, we need to extract the features, and then on those features, we will be applying basically our algorithm, either the classification, clustering, whatever it is. So if you take an example, then the things will be more clear. Consider a set of photographs. You say some images are given to us. Okay. Though technically the photographs and the images are different, but take it as a images. Consider a set of images where each image is to be classified according to whether or not it continues a human face. So what is the case? That we have been given a lot of images, a set of images is there, and in those images, few images the human face are there, and in the few images human faces are not there. The raw data is a set of pixels such as and as such is not suitable for many types of classification algorithm. And we say that we have been given the images, and we know that in computer the images are stored in the raster as a raster in a raster form, or we say the raster images, and the raster images consist of basically a pixel values. If it's a black and white, then a gray scale, it will be there 0 to 256. And if it's basically a colored image, so the three channels will be there. So it depends on the size, how many colors can be taken. Anyway, don't go into those details. So a pixel information is given. So only because we have the pixel information, on that basis, it is not possible that we can find it out that whether in the image the human face is there or not. So what we will have to do, from those pixel images, we need to find out some such aspects that by looking through those aspects, we will be able to say that whether this image consists of a human face or not. So when I say we will have to find out some aspects, so aspects means basically the features. It means we need to extract some features, and looking at those features, I mean computing on the basis of the computation of those features, we will be able to say that whether this is basically a human face or not. So that is written here. However, if the data is processed to provide the higher level features, such as the presence or the absence of the types of edges or the areas that are highly correlated with the presence of the human faces, then a much broader set of classification techniques can be applied to this problem. So those who are into the image processing, so they can understand in a much better way. Suppose if we can go for the detection of the edges and a lot of other features that we can find out, so on those basis we can say that whether a human face is there in the image or not. So this example is basically simply to tell you that if we have a raw data, so from the raw data we may need to extract the useful features on which we will work to say that what the actual output is by the our algorithm. So that is basically the feature extraction, that we need to extract the feature from the raw data. Unfortunately, the feature extraction is highly domain specific. Like for example, if you take this one, so the image is having a one format, that it's a raster image, the pixel information is given. So whatever the method, method means algorithm, whatever the algorithm I will make that will extract the feature from the raw image, if suppose a text comes to me as an input, obviously I cannot use basically those algorithms, I mean those feature extraction algorithms on the text, because the property of the text and the image is completely different. I will have to find out the different methods that will work on the text. So that is basically written here. That is the meaning of the first sentence, that the feature extraction methods are highly domain specific. It cannot be applied on the variety of the problems. Therefore, whenever the machine learning is applied to a relatively new data, a key task is the development of a new feature and the feature extraction method, means how to extract the features from that. The other one is basically a mapping the data to a new space. Okay. Now, what is this mapping a data to a new space? So a totally different view of the data can reveal the important and interesting features. And obviously it won't be possible to understand by a one sentence. So example is given here. And if suppose it is not clear by the example, then you can go through the next diagram also. Sorry, the diagram also, that will make it more clear. So what is written here? Consider the time series data, which often contains periodic patterns. If there is only a single periodic pattern and not much noise, then the pattern is easily detected. However, if there are a number of periodic patterns and a significant amount of noise is present, then these patterns are hard to detect. However, such patterns can be detected by applying the Fourier transform. Fourier transform is written only as example. A lot of other methods are also there. For example, the Veblet transform and other things are also there. That is written here also, the Veblet. The Fourier transform to the time series to change to a representation in which the frequency information is explicit. Because for the each time series, the Fourier transform produces a new data object whose attributes are related to the frequencies. So let us see it with the example to be more clear. Say what is written here, that this is basically this is a one time series data. So you see that there are two patterns here. The two different time series data is there. One is basically shown here by the solid line. You see this solid line. Okay, this solid line is here. The other pattern is basically you see by the dashed line. Okay, so there are two different time series data here into it. So here it is easy to find it out that what is basically the two patterns are there. What the two patterns are there. Okay, here what happened is that a random noise basically has been added into this. Okay, so that is written here to understand in a more better way, that this figure B is the sum of the three three time series data, two of which are shown in A, and the third time series is a random noise. So these two patterns, I mean these two time series data and a random noise, it has been added and it has become this particular figure. So you see that when a noise is added into this, now it is not at all possible to find out this particular pattern. Obviously, seeing this data, we will not be able to know that these two different patterns are there. If suppose instead of this into the Cartesian product, if I sorry, not Cartesian product, in the Cartesian coordinate system, if I represent in the polar system, that is the frequency domain system, so you see that this will be basically represented in this way. So you see that it is not possible to find any pattern or anything here, but it is possible to find what is the pattern here if we just change the domain of it. So I simply mean to say that if we change the frame of the reference, if we change the format of the data, so it may happen that something which is not visible in the one frame of reference, it may be visible in the other frame of reference. Okay, so that is basically mapping the data to a new space. Then the feature construction. So this is basically, as I was telling you the earlier, that we can club few features and we can make a one feature, then it will be much better. So this is basically, this slide tells that in a very good, with a very good example also. So sometimes the features in the original data sets have the necessary information, but it is not in a form suitable for the machine learning algorithm. In this situation, one or more new features constructed out of the original features can be more useful than the original features. Okay. Now you see this with example. What we say here in this particular paragraph, only one thing, that it may be that if we create a new feature that is more that is giving more information in comparison to the other original features which were present there. Consider a data set consisting of information about historical artifacts, which along with the other information contains the volume and mass of each artifact. For simplicity, assume that these artifacts are made of a small number of materials, for example, the wood, clay, bronze, and gold, and that we want to classify the artifacts with respect to the material by which they are made. In this case, a density feature constructed from the mass and the volume features, it means the density is equal to mass by volume, would most directly yield an accurate classification. So we say here that suppose we have some artifacts, a data of some artifacts, and it contains a volume and the mass and some other features also. Some lot of other features are also there, and the volume and mass is also there. And what is the case? That these artifacts are made up either of wood or the clay or the bronze or the gold. Okay. And we have to classify them in such a way that which artifacts are made of wood, which are clay, which are bronze, and which are gold. So we know that the density of the wood, clay, bronze, and gold are completely different. And we have the volume as well as the mass also. So if I create basically a one feature named density using the mass and volume, so it will directly give me that which belongs to which one. So that is what we have done here, that we have created basically a new feature, density, with the help of the mass and volume. So now the mass and volume is not known, the density is good enough. So this consists of the information which is contained in the mass as well as volume. So now the mass and volume has become redundant features, and this is basically the relevant feature now. Though there have been some attempts to automatically perform the feature construction by exploring simple mathematical combinations of existing attributes, the most common approach is to construct the features using the domain expertise. So here we say that the more domain expertise or the more domain knowledge you have, the more better it is that you will be able to tell that how to make the combinations to find the good combination of the attributes. But obviously, it doesn't mean that if you do not have a good domain knowledge, you cannot do that. So you can do that by the computational methods. But if you have a domain knowledge, that is much better. So I do not know. Okay, it is already 7. So only the 2 slides are there. So actually it was a 1.5 hour, later it has gone to 2 hours, and still 82 persons are here, including me. So it's good that earlier it was 89, only 7 has left. So only 2 slides are there, and I say about the missing value in these 2 slides. So it is not unusual for an object to be missing one or more attribute values. As I told you that the data is never pure, so it will have some problem. And in many cases, it may happen that it has some missing values in the attributes. So there may be various reasons for it. For example, the information was not collected. Some attributes are not applicable to all the objects. However, they should be considered seriously during the data analysis. For example, when I say that it is not applicable to all objects. So suppose I have I'm creating a database, or I'm collecting the information, and where the one field is basically the landline. So nowadays, a lot of homes are there. They have 10 mobiles, but they do not have any landline. So definitely that landline attribute value for that particular family will be blank because they do not have the landline. So it will create basically a missing value. So this is just only a one example, and we need to take the missing values very seriously, because missing values create a lot of trouble to the machine learning or the data mining algorithm, whether the classification, clustering, whatever it is, the missing values create a lot of problems. So that is why the missing values has to be handled accurately. I mean to say that if you fill it randomly, then it will impure the data. So definitely you do not have to impure the data. You have to make the data more pure. So you will have to use some mathematical formula. I mean, you will have to, you cannot do it ad hoc. You will have to use the systematic approach, so that appropriate values are basically fitted, so that the data is not corrupted, but rather the purity basically increases. So that is what we have to take care. So there are several strategies and variations of these strategies for dealing with the missing data, and each of which may be appropriate in certain circumstances. So we say that as per our use, we will see that which is more appropriate. So ways to handle the missing values data. What is one? Eliminate the data object or the attribute. So what it simply says is that suppose if there are say a large number of attributes are there, and there are very few attributes where the missing values are there. For example, as I told you that the landline phone. So if I'm collecting say 20 features, and out of the 20 features, one is landline, and landline is the only feature where some missing values are there. So I will simply remove the attribute landline, and with the rest of the 19 feature, I will do my analysis. So I just took in this example that only one is missing, but it is not so that only one attribute, it may be more than one also. I simply mean to say that if very few attributes have the missing values, you can remove those attributes altogether from the data set, and with the rest of the feature set, you do your job. Probably or most probably you will get basically the correct answers. If they are not very much important, suppose the attribute is very important, then obviously the result won't be that good. The other is the data object. Suppose if there are very few data objects which have the missing values, so you can remove those data objects altogether very easily without any disturbance. Suppose if I have a data set which consists of say 1000 data objects. Out of the 1000s, there are say hardly 30 or say 40 objects where some missing values, I mean, for some attributes, the values are missing. So I can just remove basically those 30, 40 objects, and out of 1000, the 960 or say the now 970 objects are still there. So those 30 may not be very much important, and they may not disturb the pattern or the whatever is inherent knowledge which is there in the data set. So I will be able to find it out very easily. And it may be that you may go for the removal of attributes and the removal of a object also. But definitely one has to be very careful that you cannot eliminate number of attributes, and you cannot eliminate number of objects also, because in that case, the property of the value, property of the data set will change. And if the property of the data set changes, it means you have corrupted the data. So we have not to, we do not need to corrupt the data basically. We have to rather make the data more pure. So that is one approach that we can apply. The other approach is basically estimate the missing values. And it is not always so that we cannot estimate the value. In some cases, we can estimate the values also. Suppose if it is so that the algorithm, that particular attribute is such that you cannot altogether eliminate it, but there is some way by you can find out that what is the most probable data for this one. So apply that particular method instead of removing it. So in what conditions it can be done? Some examples are given here. In a time series data, the missing values can be estimated or the interpolated by using the remaining values. Suppose if it's a time series data, so what you know, obviously if it is a time series data, so you can use the any interpolation method that you have studied in the numerical methods and analysis to find out that what can be the approximate value of this. I mean, interpolation, extrapolation, you must have studied. So you can use the interpolation method to find out the most probable value if it's a time series data. If a data set that has many similar data points, the attribute value of the points closest to the point with the missing value are often used to estimate the missing value. What it simply says is that if there are two objects which are very close to each other, when we say the two objects are very close to each other, means that the feature values of these two objects are very similar. It means they are very close to each other. So whatever is this value for the feature, if suppose this feature is missing here, so whatever is this value, so this value also will be very similar to this one. Okay, so you can just roughly take a value which is near to that one, and you can just think that, okay, this may be the most probable the value here. Okay, so you can do that. And it is not necessary that only take the one particular nearest object. You can take rather a set of the nearest object. Suppose 4, 5, or say 10 nearest objects, and then you can take average or anything of the missing attribute. I mean, suppose this is the missing attribute. The 10 are very similar. These 10 are very similar to this. So for that attribute, take these 10 values, take the average and fill it here. I mean, you can treat this average as a missing value of this because they are very closer to each other, because all other attribute values are similar. So obviously this attribute value also must be similar to that one. So you can just fill the value in this way. If the attribute is continuous, then the average attribute value of the nearest neighbor is used. If the attribute is categorical, then the most commonly occurring attribute value can be taken. And what it is here written, if it is a numerical attribute, then you can take the average. The second is that if suppose it is a categorical, so you cannot find the categorical in, you cannot find the average in the categorical. Suppose if it's a color, so red plus green plus blue by 3, you cannot do that. You're not going to find out anything. So in that case, what you can do is, out of those 10, suppose in 5, the color is red. So because the red is majority, so you can take this color value also as a red. That is what is the meaning here, that the most commonly occurring attribute value can be taken. So what it simply tells here is that there are few cases in which it is easy, or it is possible that you can find out that what may be missing value. Okay, so you can go for that. So either you eliminate the object, or you eliminate the missing value, or you estimate the missing value. The other one is ignore the missing value during analysis. So what this simply says is that I know that if there is a one particular missing value for an attribute, then it will create a problem. So what will happen when I am computing the similarity, dissimilarity, etc. Of those two of objects which consists of the missing value? So do not use that particular attribute. Suppose if there are 20 attributes, okay, and I'm finding the Euclidean distance. So if suppose all between any two objects, if all the 20 attributes are there, then you use the 20 attributes. If in one of the object, one attribute value is missing, so what you do not consider this attribute, and instead of 20 attributes, use only 19 attributes to find out the Euclidean distance. Definitely, this 19 attribute Euclidean distance will not be perfectly accurate, but obviously only one missing value is there, only one attribute has been removed, so it will not create a lot of problem. So that is what is basically ignore the missing value during the analysis if it is possible. But suppose if a large number of attribute values are missing, then definitely you cannot do that. Suppose if the 5, 6 values are missing, then only 14 attributes and the front two attributes, there may be a difference, and there may be a great difference, and especially it is not uh, uh, when it is not channelized into one range. I mean, it is not into the range of, say, for example, 0 to 1, -1 to 1. So if it is not in a range, the ranges is completely different, then it may create basically a more problem. So the last one, I mean, this one is that it is also possible that we can ignore the missing values in some cases, in some possibilities. So this was the last slide. So if you have some questions, please, you may ask. I'm ready to answer. Is there any question by anyone?
Do the participants have any question? Sir, there's